So, hello everyone. Today we are going to start another lecture on numerical analysis. Okay, so let me open up my whiteboard and let's create a new whiteboard. It's saying I have no internet connection. That's strange. Gee. Let me open it. Yeah, so numerical analysis. We need numerical analysis across all streams of aerospace engineering, especially in all streams of engineering, to be really honest. It's one of the most fundamental and core subjects that one has to study, one has to be competent in. Uh, so let's start with, well, and its application is in computational fluid mechanics, computational fluid dynamics, computational finite element analysis, calculus, advanced mathematics, linear algebra, programming, aerodynamics, solid mechanics, theoretical mechanics, physics. Okay, numerical solution is usually solved abstract models of nature, differential and integral equations, linear and non-linear equations. Okay, so we will be solving. There's my pen, please. Oh, differential and integral equations. Differential and integral equation. The most horrible plan. And linear and non-linear equations. Non-linear. So, why do we need to do numerical analysis? For example, to verify our results, to actually understand how analytically our systems behave, to find out analytical solutions, to compute and make approximations. With this, we can do simulations, but disclaimer here: simulation is not equal to reality, and each and every numerical analysis has got an error, and we have to quantify that error as well. Okay, so we shall begin our lecture with some mathematical preliminaries, limits and continuity, integration, Taylor, and polynomial series. Okay, so limit. What is limit? Limit. A function f defined on a set x belongs to R has a limit L at C belongs to x, written as limit x belongs to C f x is equal to L, such that epsilon is greater than 0 and at epsilon. So we'll do a quick Google search, and I'm gonna paste the definition over here so that you can see it. Okay. And I don't know if I can pan this. I just need to take it over there. Okay, so here we got limit. Here we got limit, and now let's see what all things it could offer us. Let me close my sticky notes. Okay, so yeah, explain each and every terminal. So yeah, so first, what are we trying to say? What we want to understand, what does it mean for a function to behave nicely near a point? This is what limit is about. What does it mean for a function to behave nicely around a point? The statement cleaned up a bit is limit uh, x belongs to C, x to C, fx equal to L. Okay, I should change. Maybe make it 2 and get a better color here. Yeah, this one's better. As x, meaning what does that mean? As x gets closer to C, fx gets closer to L. When x gets uh, closer to C, fx gets closer to L. Now now let's break every item so that I can explain it to you. A function, remember always, a function is just a machine. It takes an input, gives an output. It takes multiple inputs, gives multiple outputs, or takes multiple inputs or gives a single output. That's a function. For example, fx is equal to fx square. Okay, fx is equal to x square. Now if I give x is equal to 3, x equal to 3, I get f of 3 equal to 9. Okay, uh, if x is equal to 2, then fx is equal to 4, for example. And now set x belongs to R. X, now this symbol here, this is the symbol for belongs to. So for example, if x is a collection of numbers, collection of numbers, x is a collection of numbers, all numbers are real, as we said, x is a collection of real numbers, real numbers. So x could be like, let's say for example, 0 to 20. Okay, inclusive, both inclusive. Or a point C, and then we have a point C. Now C is a specific number inside this set. For example, if x belongs to 0 to 10, then C equal to, let's say, 5. limit value L. This is the number that fx is approaching. Important. L is not necessarily equal to f of c. The real meaning, core idea is if we take x very close to c, okay, then fx becomes very close to L. Then fx becomes very close to L. Now the definition is this weird thing. Let me write it down completely. Let me write it down. I don't know what these signs are called, but let's try. Epsilon greater than 0. This is greater than, okay. Delta greater than 0 such that x minus c is less than delta. This implies that fx minus L modulo is less than epsilon. Now let's decode. Can you make fx as close as I want to L? Yes, just make x as close as possible to c. For now now let's explain each and every symbol. What does this thing mean? Epsilon greater than 0. For every small number epsilon. Now epsilon is a very small number. Epsilon, and it could be epsilon, usually it could be 0 0.1, 0 0.001, 0 0.000001. Okay, okay, we don't choose it, someone else does. Okay, so and the next symbol is, let's write, okay, let's write this, inverted e, mirror image of e greater than 0. There exists some small number delta. Delta is how close x must be to c. Delta indicates how close x must be to c. And we choose delta. Let me write it in red. We choose delta. We choose delta. Okay, epsilon is chosen by someone else. This is actually the tolerance. I mean, we can also choose it, but it is the amount of accuracy precision that we want in our computation. Mod x minus c should be less than delta. Third, let's go to third. Mod x minus c, mod x minus c is less than delta. Distance between x and c is small. So for example, if you are trying to find out the limit at c equal to 5, so So our x could be like 5.1 or 4.9. Okay, now here we are getting into real some, and then what is, so this is the input, and then what is the output is fx minus L should be less than our desired tolerance, right? It's the distance between uh, how much tolerant are we regarding our solution. Okay, so let's say fx is equal to x square. Let's take a simple example. Fx equal to x square and c equal to 2, and so what we are trying to find out is limit x tends to 2x square, uh, which is equal to 4, obviously. X, so if I say x equal to 2.1, then it becomes 4.41, and x equal to 1.9, so fx becomes 3.96, 3.9601. Very close. Okay, very close. Very close. Final integration epsilon, how close to you, epsilon is how close, uh, epsilon is how close you want the output to be. How close you want the output to be, and delta is how close you must take the input. How close you must take the input. Can I write over? No. Let me put my face up here somewhere. Okay. A limit means by making the input close enough to C, we can make output as close to L. Okay. Yeah. So let's see this with the help of a graph. Okay. Uh, let's see with the help of a graph, and ChatGPT is going to help us here. Okay, just throw it out. Let's see if we have some beautiful images. Uh, yeah, this one's nice. This one is also nice. Let me use this one. So you see this green area, 3 minus delta and 3 plus delta, and this is our epsilon. Okay, so yeah, got it, I got it now. uh, uh, 3 minus delta, and this is 3 plus delta. And then we have uh, like it's approaching to f of 3 is f of 3 no, limit x approaches to 3, f of x equal to 2. So if I take a small number, let's say x barabar 2.9, then our fx would be a little less than 2, let's say 1.98, and if x barabar 3.1, if x would be equal to let's say 2.23. Okay, so this shows the relation between input and output. Okay, L minus, and actually this is the best example which would show you. Let me draw another image. And let's span it, take it over there and paste it. Best example, you see, uh, x naught minus delta. If I'm at x naught minus delta, then this is the value. And if I'm at x naught plus delta, then this is the value. And L, this is the limit at x naught. Limits and continuity. A function f is defined on set x belongs to or has limit L at x belongs c belongs to x, written as limit x belongs to c f x is equal to L if a small difference greater than 0, if tolerance delta tolerance is greater than 0, and epsilon delta is greater than 0. Okay, let me just ask, what do these weird signs mean? The first meaning, this means for all, for every, no exceptions, everything is included for us. Okay, so we had to know some of the meanings of this. Means for all, for everything, everything included, for all epsilon greater than 0. Now similarly, let me ask for this thing as well. Hmm. So what this condition actually tells us, for all epsilon greater than 0. So this means no matter how small the epsilon is, but being greater than 0, the condition still holds. The symbol, this means there exists, okay, this inverted mirror image E, it means there exists delta greater than 0. That means there exists delta greater than 0. uh, there is at least there, or we can say, or there is at least one, or there is at least one one delta greater than 0, such that x minus c is less than delta. This implies that fx minus f of c is less than epsilon. Let f be continuity on a point. Now let's discuss. There exists, there is at least, this means there is at least, I need my water. Where is my water? Oh no. Guys, I need to take a break for water break. Sorry. Okay, so where were we? Yeah, we were discussing continuity. Let f be a function defined on set x belongs to R and C belongs to x, then f is continuous at C. Limit limit x belongs to C, x belongs to C, f x is equal to f of C. Okay, limit and continuity. A function is continuous on set x belongs to R, that is f belongs to Cx if f is continuous at each point. So suppose I have a set x belongs to R, x belongs to R. If f is continuous, f is on at each point, at each point, at each point, sub x belongs to small x belongs to capital X. Okay, now let's get on to some theorems. Okay, if f is a function defined on set x belongs to R and C belongs to X, then the following statements are equivalent. So if Cx belongs to R and C belong X is a set. This what this means is X is a set of real numbers. Okay, and C belongs to X, which means it's one of the real numbers that is belonging to the set X, then the following statements are true. Then what statements are true? F is continuous at C, F is continuous at C, cont at C, and if xn n equal to 1 to infinite is any sequence in x, is any sequence in x converging to C, then limit n belongs to infinite, f of xn is equal to f of C. Now let's hold on for a while and see what does this have to mean. If xn n equal to 1 is any sequence in x converging to C, okay, if it's converging, then limit n tends to infinite, f of xn is equal to f of C. Okay, limits and continuity, limit and continuity. Now we get on to differentiability. A function f defined on open interval I containing C, then f is differentiable at C if f is differentiable if if let me use a black pen instead of a little thicker one, and I think so if I can use a much thicker one, f dash c is equal to limit x belongs to c, x belongs to c, f of x minus f of c, x minus c. Exist. If the limit exists, we call f dash c a derivative. If this limit exists, if this condition holds true, uh, if true, if true, then fx is differentiable. See, a function that has a derivative at each number in a set x is differentiable on x. If x is differentiable, if x is differentiable at c, then then f is also continuous at c. If f is uh, differentiable at c, then f is continuous on c. So let me show you some examples. Like for example, we have here a smooth tidy function. Suppose this is the point c. So this function, if I go a little bit left to the function, are there values existing? Yes. A little bit ahead, values are existing. Yes. So this is continuous, and hence f of x minus f of c. This limit is existing, that's why this is differentiable. Now let me show you another example, because I can find a slope at this point. This is the slope, f of x minus f of c, f of x minus f of c upon x minus c. This is the slope, okay. So but for example, if I have a function like this, now here it is continuous, but it is not differentiable, but because I can have any type of slope, I can make any type of slope through this point. Okay. So in such a case, fx is continuous, but not differentiable, if f is differentiable at c, then f is continuous at c. Now let's go to Rolle's theorem. Important things, very important things. Rolle's theorem. Rolle's theorem, mean value theorem. Okay, suppose let me actually just paste these things down, and then I'll try to write it. It's a bit difficult to write with this tablet. And paste, delete, and paste. What's that? So suppose f belongs to closed interval. Suppose f belongs to closed interval. F belongs to closed interval. This is a c, a comma b. What's the thickness of mine? Let's keep it 4. And f is differentiable on a and b, and f is differentiable, differentiable open bracket a to b open bracket open bracket if f of a equal to f of b, if f of a equal to f of b, then a number c exists between a and b, then there exists a number c belongs to a and b. So c could not be equal to a. This implies that c not equal to a comma b with f dash c equal to 0. So what it is actually trying to say is, suppose f is differentiable in a comma b. So what is it is actually trying to say is, if I have a function and it is defined, let's say this is the function, and f of a equal to f of b, such that f of a equal to f of b. So so we have to take a function, like for example, let's say let's take a convex function. So f of a, this is f of b. So there will be a point c here where f dash c equal to 0, as we can see the slope is 0. So this is what is Rolle's theorem. And if f of a equal to f of b, these two things are equal. But in such a case, f of a is not equal to f of b, so we cannot guarantee that we have a point between a and b where f dash c equal to 0. Then we go to mean value theorem. So this was Rolle's theorem. Rolle's theorem. And I think so it's pretty intuitive. I mean, how else could we make f of a equal to f of b if there is no point where the slope, there is no one unique point where the slope is equal to 0. Like for example, if I have such a function, okay, so like let's say a and b, so this point the value of the function is same, so there exists a point c over here where f dash c equal to 0. Okay, if mean value theorem, if c belongs to ab and f is differentiable on ab, then now let's span our screen. Okay, mean value theorem. If f f belongs to c a comma b, and f is differentiable, and f is differentiable on ab and on a comma b, then there is a number, then there is c belongs to a comma b where f dash c is equal to f of b minus f of a upon b minus a. So let's see, is differentiable on when we when there exists a number such that f dash c is equal to f of p. So here we do not have any. Let's take a simple convex example. Let's say uh, let's take x square only. So this 2, this is 4, and this is oh, if I'm taking x square, then it should be like this. Okay, like this. So 2, 4. So what it is actually trying to say is f of p is 16 minus 4 upon 4 minus 2, which is equal to 12 by 2 barabar 6. So f dash and any point. So there is a point in between f dash c whose slope is going to be 6. So I don't know. This is mean value theorem. Okay, I get it. Mean value theorem. So mean value theorem, it connects average change with instantaneous change. It sometimes moves smoothly from point A to point B. There is at least one moment where its instantaneous speed equals to the average speed. This is what it means. The secant line connects 2 points. Let's see if we can have some differentiable, no sharp corners, cuts, right side, left side, what really. It says somewhere between A and B, instant slope is equal to average slope. Alright, so okay, at every point across this curve we will have different slopes. Okay, at every point we will have different slopes. Okay, so what it is saying, there is a point C, there is a point C where instantaneous slope slope is equal to average slope. Average slope. So this is a big approximation by here. Okay. So now let's see if we can get some good examples. Let me understand. X tangent x is secant. Okay, so what it is saying is that if I connect f of a and b, let me draw a more sharper example. So for example, let's get on with this. So this is 2, this is 4. If I connect both of them, so there will be one point between these 2 points whose slope would be equal to the slope of the secant. Okay, let me show you this with a nice example. Okay, so you see f of a, f of b, and there is a secant line. So that's the slope between these 2 points, or kind of the average slope. And so there will always exist a point tangent to which the line would always be parallel to a secant line, which means the slopes are equal. I mean, you understand my point. Okay, so this is Rolle's theorem, and we have got mean value theorem, and then we have extreme value theorem. Okay, so extreme value theorem would be our last bit for the day, and then we're going to wrap up for this video. Extreme value theorem. That's right. Extreme value theorem. If f belongs to CAB, the C1 comma C2 belongs to AB exists with if f belongs to CAB, the C1 C2 such that they belong to A and B exists with f of C less than f of x is less than f of C2, f of C1 less than f of x less than f of C2 for all x belongs to A and B. In addition, if f is differentiable on A and B, the number C1 and C2 occur either in the endpoints of A and B, or where f dash is 0. So okay, that's a lot to that's a lot to digest in one go, so we're going to break it down. Explain. Extreme value theorem tells you something very reassuring about nice functions. A continuous function on a closed interval always reaches the highest and the lowest value. Okay, if you draw a curve without lifting your pen on a finite interval, then you must have a maximum and a minimum point. Okay, let's see if this thing could be supported by some statements, some graphs. Global minimum, critical points, and global maximum. So extreme value theorem says that what extreme value theorem is saying is that if there is I draw a curve like this. So let's do it like this as well. So between A and B, so between A and B, there will be a point which would be less than A, and there will be a point which would be greater than B. Critical points. Okay. Global maximum, global minimum is equal to a graphical representation of extreme value theorem. Let's try to understand extreme value theorem with this. So here we see a graph f has an absolute maximum at 8, 12. F has an absolute minimum at -1, -2. F has a relative maximum at 2, 9. F has a relative minimum at or local minimum at 5, 3. It says maths main exists. It is okay to omit absolute. This is understood. I don't know what they're trying to say by this. Let me find another graph. F of C, F of t. So the point is, if you draw a graph between A and B, uh, so the whole point is that without lifting up your pen, if you draw a graph uh, between A and B, okay, like A and B, so there will be a point C which would be greater than and both of these and a point D, here we are calling them C1 and C2, by the way. C1 and C2, C1, C2, and C1 comma C2 belongs to A comma B. Yeah, so yes, so C1 and C2, so C1 and C2, where would they occur? Either they could occur on the endpoint. So for example, if I draw a graph like this, okay, so this is A, B, A, B, so it's existing here within A comma B, or where the slope is 0, or where so C1 and C2, C1 and C2 can be equal to A comma B, like we saw here, or where the slope is equal to 0. Here the slope is 0, here the slope is 0. So this is extreme value theorem. Now from generalized Rolle theorem, I think so we'll carry on in the next class. I hope so. You guys don't mind. It was a pleasure explaining and devoting some time here. Hope you get something, and hope I get to understand things better. Thank you very much. See you next time.